in the chat. Pay attention to the chat function throughout the course of the presentation. That's where you can read comments and add comments and ask questions. Dan Snyder's got a message there, and he'll be monitoring that throughout the course of the meeting today. And the last thing I'd like to say is anyone that wishes to have their certificates for this presentation, please make sure you email Cindy Pascal, and I'll type her email in the chat box before the end of this session, and that'll make sure that we have the correct email to send you a certificate to. So with that, I'm done, and Dr. Barker, the floor is yours.
All right, well, let's get this party started. I also want to welcome you to the Council of Forest Engineering webinar series. I am Michael Barker from the University of Wyoming, which is quite a ways west of probably almost all of you, since you guys are in the Northeast there. And I'm also the Director of Education for the Short Span Steel Bridge Alliance. So for an opening statement, state and county owners, and here forest engineers, are replacing and need to replace many older and deteriorated bridges in their inventories. A common concern they face is selecting bridge material, construction techniques, and protection systems that'll perform well throughout the bridge service life and yet make economical sense within their limited bridge replacement budgets. Today, we're going to talk primarily about simple span bridges in the short span range. This represents the bulk of local bridges and a significant percentage of state bridges across the country. So I'm going to be offering two presentations, one today and one on Friday, January 29th, same time, same Zoom link. This first one is on Short Span Steel Bridge Alliance and the economy of steel bridges, considering first costs and life cycle costs. I'm also going to introduce standard simple span steel bridge designs developed through the Short Span Steel Bridge Alliance, so owners and engineers can consider and quickly compare steel and concrete bridge alternatives. The second presentation on January 29th is a favorite of mine, and one that is a little more exciting than talking about costs. So I'm looking forward to seeing you on the 29th. We're going to look at a showcase of bridge case studies that manufacturing firms can design, build, and deliver to the bridge site. These bridge manufacturing firms use experience and economies of scale to produce high quality, beautiful, functional, and economical bridges for owners across the country. So here's the plan for this first presentation. We will introduce the Short Span Steel Bridge Alliance and its purpose and functions. Of course, one of its functions is to represent the design and construction of simple span steel bridges. As part of that, we will look at cost competitiveness of steel bridges for first costs and life cycle costs. Then we're going to finish with a presentation on what's called eSPAN140, an online tool for preliminary steel bridge design for simple span bridges up to 140 foot in length, so that steel and concrete bridge alternatives can be compared easily without an undue and costly design for the steel bridge. So the Short Span Steel Bridge Alliance is an industry support alliance that is, quote, as I show here, a group of bridge and buried soil structure industry leaders who have joined together to provide educational information on the design and construction of short span steel bridges and installations up to 140 feet in length. The purpose is to help owners and design engineers with designing and building simple span steel bridges. The Alliance was initiated in 2007 as part of the American Iron and Steel Institute, where the members are stakeholders in the steel bridge industry. The Alliance was formed to address two main concerns with the construction of steel bridges. The first is a misconception across the United States that for shorter span bridges, concrete is always less expensive than steel. The second issue is that concrete bridge design is easy using charts and tables, whereas a steel bridge design is an individual piece of art for each design. So the Alliance has developed economical studies that address the first cost and life cycle costs of steel and concrete bridges that show both steel and concrete bridges are competitive. The goal is to break that preconception that concrete is always less expensive. And we're going to look at those studies here. The Alliance has also developed standard simple span steel bridge designs for bridges up to 140 feet, so that when an owner or engineer is considering the design for a short span bridge, the steel design and concrete design can be quickly developed and compared without the effort of designing the steel bridge. We're going to look at these standard designs in what is called eSPAN140. The Alliance is involved with all aspects of simple span steel bridge design and construction, including outreach and education. Example of that is today's webinar. Resources on all aspects of steel bridges, sample case studies, the simple design tool eSPAN140, innovative and accelerated bridge construction solutions, which we're going to look at on January 29th when we look at manufacturers that can deliver you a bridge. www.shortspansteelbridges.org, like Dan talked about before we started, that website is the go-to location where a user can interact with the Short Span Steel Bridge Alliance. So we start with that preconception that concrete bridges are less expensive than steel bridges in the short span market. Many owners and engineers believe this to be true, and many times steel is not even considered when there is a short span bridge need. This is really unfortunate because that means owners may be paying more for their bridges than is necessary. If owners and engineers would compete steel and concrete bridges, the cost for both would be lower due to that competition. In fact, studies show that states or regions that do not even consider steel alternatives and only build concrete bridges pay more for those concrete bridges than states or regions that have a healthy competition between the two bridge materials. So now we're going to look at case studies of county and state bridges. The first case study is from Audrain County, Missouri, from 2012. These two bridges were built by an Audrain County work crew, so there is no contractor for the bridges. This is a special case study in that the Short Span Steel Bridge Alliance worked with the county engineer from before construction through the opening of the bridge to track the costs. The Steel Bridge Missouri Bridge 411 on the left here consists of 4 steel girders, a 47.5-foot span, a 24-foot roadway width, and a 2-foot structural depth. The concrete bridge, Missouri Bridge 336 on the right, consists of 6 precast hollow core slabs with a 50.5-foot span, a 24-foot roadway, and a 2-foot structural depth. These two bridges were built in the same year and are nearly identical except for a small difference in the span length. So the engineer was asked to keep a detailed account of the cost for the construction of the two bridges so that a direct comparison could be evaluated. This slide shows the total cost of the two bridges where the costs are broken into material, labor, equipment, guardrail, rock, and engineering. And we can see that for the total cost of these two bridges, the steel bridge has a 19.3% savings over the concrete bridge. The costs are calculated based on square footage of the deck area for an equivalent comparison since the concrete bridge is 3 foot longer. However, comparing only total costs can be deceiving given the different site characteristics of the two bridges. For instance, we see here that the concrete bridge had significantly higher engineering costs and lower rock costs. So to be more fair and do a better comparison, the engineer was also asked to separate out only the superstructure costs so that an equivalent direct comparison could be made for the two bridges. These costs shown here represents the costs associated with only the superstructure. So this is a true apples to apples comparison of the cost for these concrete and steel bridges. Removed from the total cost is all site prep work, grading, engineering, rock, abutments, and so forth. And we can see the cost for the materials, labor, and equipment for only the superstructure. And we see that the steel bridge costs $37.50 per square foot and the concrete bridge costs $50.61. The steel bridge is considerably less expensive for this comparison. One item to note is the equipment cost, where the steel bridge used a county-owned 30-ton crane. The concrete bridge girder members are heavy, and the county had to rent a 100-ton crane at a cost of $3,500. The other $500 for each under the equipment is a rented skid steer for incidental work. However, even if the county needed to rent, and I'm looking at the bottom of this slide here, even if they needed to rent the 30-ton crane at a cost of about $1,500, that increases the steel bridge cost to only $38.88, still considerably less than the concrete bridge cost. The steel girders are weathering steel that requires no painting, and these costs are already in the cost of the steel girders. If the county needed additional corrosion protection and used, for instance, galvanizing, the cost at that time was approximately 22 cents per pound of steel, and the steel bridge total cost would still be significantly less than the concrete bridge costs. So as kind of a summary for these two bridges, as they were built, the superstructure only costs show that the steel bridge option would have a savings of over 25% compared to the concrete bridge. That is 5 steel bridges for the cost of 4 concrete bridges. This is for 2 almost identical bridges where they have the same structural depth, which means no difference in approach work, the same roadway width, the same guardrail system, the same abutments, and the same county crew built both bridges. So this demonstrates that steel is competitive with concrete, and that preconception that concrete is always less expensive is incorrect. Steel short span bridges can and many times will be less expensive than the concrete option. The reason for these economies for steel bridges vary over the bridge fabrication and construction process. For instance, we saw that one reason steel is competitive is that the equipment requirements are less, since steel bridge components are considerably lighter than concrete components. For steel bridges, the dead load is significantly lighter and lighter abutments can be used, or even some of the economical modular abutment systems can be employed. Another benefit for the economy of steel bridges is the use of partial depth precast panels or corrugated metal deck systems that make the casting of the concrete deck efficient. Now, we know that steel is a versatile material and that steel bridges can be made in many forms with complicated details in fabrication. However, these simple span bridges are simple span bridges and do not require complicated stiffener and diaphragm details. Simple details are cost effective and easy to fabricate and erect. Another costly component for bridges are rocker or pot bearings at the girder ends. For these simple bridges, simple elastomeric bearings can be used and smaller bearings used due to the lighter weight of the structure. And of course, jointless decks with integral abutments leads to much lower deterioration rates and maintenance costs in the future. Finally, one of the costs for steel bridges is corrosion protection, since unprotected steel rusts. However, weathering steel, when applicable, is low cost and requires little maintenance for long-term corrosion protection. If weathering steel is not applicable, galvanizing, metallizing, painting, or even the use of stainless steel may be a cost-effective method for corrosion control. So that was one example. And of course, when I talk about that, people say, Barker, that's only one example. So the Alliance also worked with that county engineer on other bridges built near the same time frame. This table looks at total constructed costs of an additional 5 steel and 4 concrete bridges in Audrain County. At the bottom row of the table, we see that when we look at cost per square foot, we see that sometimes steel is less expensive and sometimes concrete is less expensive. This is healthy competitiveness and is good for the owner. These are examples of county bridges that show that both steel and concrete are competitive in the short span market, and both should be considered. Not shown here due to time, the Short Span Steel Bridge Alliance has many more similar examples. These examples were county-owned bridges. Next, we're going to look at a couple of state bridges, still in Missouri. Again, here are 2 nearly identical bridges, one steel and one concrete, that cross over the same highway near Columbia, Missouri, where I used to live. Both are 2-span with the concrete bridge just a little longer and a little bit wider. So the total cost will be divided by the deck area again for comparison. These were both design bid build projects with a contractor constructing the bridges. So here are the costs for the two bridges. Now both had non-bridge items such as conduit systems, a pedestrian fence, an architectural facade, and these costs were removed as shown here in green from the total cost since they are not structural. We see that the concrete bridge comes in at $77.71 per square foot and the steel bridge costs $72.94. However, there is a 5-year difference in when these two bridges were built. The concrete bridge was built in 2011 and the steel bridge was built in 2007. So to account for the age difference and inflation, an Engineering News Record construction cost index of 2.7% per year was used to bring the costs up to a common year of 2017. And here we see that the steel bridge was less cost at $85.58 than the concrete bridge at $91.18. So I went through all this because of that preconception. So from what we have seen here, and with many more examples not shown here, we see that steel is competitive with concrete bridges in the short span market, and that owners and engineers should consider both materials for their bridge needs. That this preconception that concrete is always less expensive is a misconception. Both are competitive, and competition is good for the owner and the public. So that's the first part of my presentation. Now I'm going to say first cost is just that, the cost for putting the bridge in place. And responsible owners are also concerned about future maintenance costs and service life. The question about life cycle costs routinely comes up. What is actually asked is, which type of bridge is best for life cycle costs? And both the steel industry and the concrete industry have offered anecdotal evidence, but has not, I like to say until now, had good evidence on which bridge type is best. So a study was conducted that examines the historical life service, meaning performance and maintenance, and the historical agency life cycle costs, meaning the true cost for building and maintaining the bridge over its life, of steel and concrete bridges in Pennsylvania. A historical study was conducted so that the results show what actually happened to the bridges instead of anecdotal guesswork from the steel and concrete industries. Now, the Pennsylvania DOT had good records of their bridges and offered the PennDOT data for their study, and I certainly want to acknowledge them. So to determine a life cycle cost for a bridge, one needs to know the full history of that bridge. This includes the initial costs and the year it was built and all maintenance that occurred over the life, including department and contractor maintenance. And of course, the lifespan of the bridge or when it will be replaced. And since I did the study, since I used the PennDOT database, all of the bridges in the database were still in service. So an end of life model is needed to estimate the life of the bridge. The study's objective was to compare life cycle costs of typical concrete and steel bridges. So there were criteria that each bridge had to meet to be included in the study. The criteria included considering only typical steel and typical concrete bridges where that was selected as precast I-beam, precast box where the boxes were adjacent to each other, precast boxes where the boxes were spaced apart, steel rolled beam and steel plate girder bridges. In addition, both precast concrete became a mainstream construction method, and modern steel design and detailing started in about 1960. So bridges built after 1960 were considered. Each bridge that was used in the database had to have complete records for initial costs and date built and accurate dates and costs for any type of maintenance, whether it was department or contractor maintenance. Since the study was looking for typical bridges, it removed any bridges that had exceedingly high or exceedingly low initial costs. And all the costs that were used in the study are based on the PennDOT recorded costs. So PennDOT has over 25,000 bridges in their database. Of those, almost 8,500 are of the 5 types considered in the study. And of those 8,500, over 6,500 were built between 1960 and 2010 for a potential study database. When these 6587 bridges were subject to the criteria, many of them did not have accurate and complete life history information, which left a database of a little over 1,700 for the life cycle cost study. This is over 25% of the potential bridges represented in the life cycle cost study, which is a pretty good representation. All of the 1,700 bridges are still in service, so a bridge life model needed to be developed to predict when the bridge would be taken out of service or replaced. The model is based on the inspection superstructure condition rating, which varies from 0 to 9, 9 being a perfect bridge, and I don't even know what a 0 is, never seen one. So it was assumed that the bridge had a rating of 9 when it was built. So I'm looking at that top right equation up there. A deterioration rate was determined based on the condition rating in the year of 2014 by the change in rating divided by the years, 2014 being the base year of the study. With the deterioration rate, the remaining life could be estimated by assuming the bridge would be replaced when the superstructure condition rating became a 3. Now I'm looking at that second equation on the top right. And then finally, that last equation up there, the bridge life is the sum of the remaining life added to the current age. So now I have the first results table from the life cycle cost study. It shows the average deteriorations rates for the 5 types of bridges for not only the 1,700 bridges, but for the over 8,500 potential bridges. I could do the deterioration rates for those. Now, in this presentation, when these result tables are shown, there will be 2 aspects of the results mentioned. First, the top 2 best performing types of bridges will be highlighted. Down there on the bottom right, we see steel rolled and precast box spread. Steel rolled beam bridges have at the lowest deterioration of 7.1% of a condition rating per year, and precast box spread box bridges is second with an 8% deterioration rate. The second aspect is the statement at the bottom left that all are similar with none way out of balance. The results show that the deterioration rates for all 5 types of bridges are not far off from each other. There is no one type of bridge that greatly outperforms the other, nor is there a type that is significantly less than the others. And I'm going to address this statement. All are similar, none way out of balance towards the end of the presentation. So we're going to look at the life cycle, a life cycle analysis of an example bridge to demonstrate the work of the study. The bridge is a precast spread box bridge built in 1969 with 3 spans and a deck area of 7,600 square feet. In 2014, the base year for the study, the superstructure condition rating was a 5. Knowing the average deterioration rate for spread box bridges is 8%, the estimated remaining life when the condition rating reaches a 3 is 25 years. Given that the bridge is 45 years old, the predicted lifespan of the bridge is 70 years. Here are the costs. The top of this slide shows the actual years and costs for the initial construction and the maintenance over the lifespan. The actual costs are divided by the deck area for comparison to other bridges. To compare life cycle costs over the database, inflation has to be taken into consideration. So all of the bridges were assumed to be built in 2014, and all of the costs inflated by the engineering news record construction cost indices, like we saw for the earlier case study. So this bridge in 2014 dollars cost $143.45 per square foot, and the maintenance costs in 2014 dollars occurred at years 19, 40, and 44. The study uses constant 2014 dollars for all future costs since the discount rate considers inflation for the future. So now the life cycle of the bridge can be developed with dates and costs in 2014 dollars. Using a discount rate from the Federal Office of Management and Budget of 2.3% that takes into consideration inflation of the future 2014 dollar costs, a present value cost of the bridge's life cycle can be determined to be $154.50 per square foot by discounting the future costs to the year 2014. This means that if $154.50 per square foot was put away when the bridge was built, the amount could pay for the initial costs and all future costs for that bridge cycle. However, we cannot compare the present value cost of a bridge that lasts 70 years to a bridge that lasts only 40 years because the outcomes are not equal. A way to compare different lifespan bridges is to use perpetual present value costs, also called capitalized costs, by assuming the bridge is replaced after each cycle in perpetuity. For this bridge, the capitalized cost is $194 per square foot, which means if that amount was put away today, it could pay for the first cycle of the bridge and replacement of that bridge every 70 years forever. With capitalized costs, we can now compare all of the bridges in the database directly. To further make sure, the study compared typical bridges for the 5 types of bridges. Bridges that had capitalized costs outside of 1 standard deviation from the mean of the bridge type were removed. That's a statistical thing we like to do, but I can tell you, even when I just left everything in there, the results did not change. This left almost 1,200 bridges of the 5 different types that were used to study the results. The bridge database was organized by bridge type in 3 Excel worksheets for each type. The first worksheet was the bridge information with location, years built, number of spans, bridge length, deck area, geometry, and bridge materials. The second was the department and external contractor maintenance performed on the bridge. And the third was the initial and life cycle cost results. So the studies and the final report were produced from this database of bridges. So now, what did we do? The report considered bridge life and capitalized costs, where the capitalized costs were studied for several variables as shown. Here in this presentation, we will look at bridge life, capitalized costs for the entire database, and capitalized costs for short length bridges, as shown here in blue. But the full detailed report can be found at that website, shortspansteelbridges.org. After this study was completed, an additional study was performed to look at the life cycle costs of galvanized steel bridges, and that report can also be found on the website. So here's another results table. For bridge life, the database of the 5 types of bridges show that the rolled beam bridges have the longest predicted life at over 81 years, and second was the precast spread box bridges at just under 80 years. However, again, none of the bridge types varied much from the others, with a 7-year spread at the bottom and at the bottom is that statement that all are similar with none way out of balance. So those are averages. I think a good way to look at predicted life that considers not only the average life, but also the standard deviation of the life is what's called a statistical cumulative density function, or CDF here. Here it is assumed that the data is normally distributed. With the CDF, a question can be asked. What is the probability that a given type of bridge will last at least 75 years, which is the expectation for modern bridge construction? The results of this show that there is a 73% chance that a rolled beam bridge will last at least 75 years, and a 65.6% chance that a precast spread box bridge will. Those were the top 2 performers for life. However, when we consider not only the average, but the standard deviation, it also shows, according to this data, there is only a 44.3% chance that the precast I-beam bridge will last 75 years or more, which was a little surprising. Next, this table shows the results for capitalized costs for all the bridges in the database. Capitalized costs here are under that column PPVC, perpetual present value cost. Here we see that the precast I-beam bridge has the lowest capitalized cost, and the steel rolled beam is second. The table also shows in the additional columns the initial cost, the present value cost of future maintenance, the average length of the bridges in that in that type of bridge database: average number of spans, average year built, and average life. This is where we need to be careful with comparisons. Directly comparing all of the bridges without considering the differences in these variables can lead to misleading results. For instance, plate girder bridges in the database have an average of over 4 spans per bridge, whereas adjacent box precast bridges average just over 1 span per bridge. Number of spans, along with average length of the bridge, along with other variables, has a significant impact on costs. In a couple of slides, I'm going to look at a more consistent set of bridges based on span length for a more consistent comparison. And of course, the full report examines these different variables in depth. However, for the full database results, we can use that CDF again to ask the question: what is the probability that a bridge type has a capitalized cost less than $300 per square foot? Now, I know you coffee guys are sitting there going, $300 per square foot, that's way too expensive. Yeah, that's right. Pennsylvania pays a lot for their bridges, but the comparison is still valid. So the CDF, the results show that there's a 93% chance that a precast I-beam and an 88% chance that a steel rolled beam bridge have capitalized costs less than $300 per square foot in Pennsylvania. So the short span steel bridge alliance defines short span as simple spans 140 foot or less. This table reduces the full database to only bridges with lengths of 140 foot or less. It does not restrict it to simple spans, but only by the length. The simple span one is in the report. There is much more consistency in the average length, the average number of spans, which makes a better comparison than the full database results. Here we see that steel rolled beam bridges has the lowest capitalized costs at $266.24, with precast spread box bridges at $272.64. However, there's still that statement down there that all are similar with none way out of balance. The plate girders come in a little high, but that would be expected in these short spans since plate girder bridges aren't as economical as rolled shapes below about 80 feet. So we expect that one to be a little high. So now, back to the original question from owners of which type of bridge is best for life cycle costs? Precast box adjacent, steel plate girder, precast box spread, precast I-beam, or steel rolled beam bridges? And this is where we come back to that statement that all are similar with none way out of balance. The overall weighted average capitalized cost for the 5 types of bridges shown up towards the top in the middle is $252.40 per square foot. Each bridge type average is within 14% of that weighted average. Knowing, now I'm on the left side about halfway down, knowing that the standard deviations for the different bridge types range from $48 to over $65 per square foot, or a better way to look at that is with coefficients of variation ranging between 20 and 25%, that coefficient of variation 20 to 25% compared to within the average of 14% means that any one type of bridge may be the most economical for a given bridge project. There is no one type of bridge that clearly beats the others. And so the conclusions of the life cycle cost part of this presentation are that typical concrete and steel bridges are competitive on initial costs, future costs, life cycle costs, and bridge life. For any given bridge project, concrete or steel bridge types may be the most economical. Again, that preconception that concrete is always less expensive is a misconception. And then I even bolded it because this is the big conclusion. Owners should consider both steel and concrete alternatives for individual bridge projects. Competition between steel and concrete bridges is healthy for the bridge industry, the owner, and the public. So next we're going to look at the easy online and free eSPAN140 software package that can give a designer a preliminary steel bridge design in a matter of minutes. If we are going to consider both steel and concrete for every bridge project, we need an easy method to produce a preliminary steel bridge design for comparison to concrete. Because as mentioned earlier, one of the objectives of the Short Span Steel Bridge Alliance is to develop standard simple span, rolled beam, and plate girder bridge designs. And with eSPAN140, an owner or an engineer can produce a steel bridge design in just a few minutes that meets all the AASHTO requirements. The standard designs use common rolled beam and common plate sizes and simple details for economy. The designs are for span lengths from 20 foot to 140 foot in 5-foot increments, and 4 different girder spacings are considered. The standard designs give the engineer the girder design, including fabrication details, shear stud and stiffener layouts, cross frame design, the deck design, and the end bearing design. For plate girder bridges, the solution will produce homogeneous girders where the web and flanges are built from 50 KSI material. For rolled beam bridges, the solution gives both a lightest weight design and a limited depth design. When replacing existing bridges, many times a smaller depth is more economical overall, even though the steel weight is heavier, because with a smaller depth, existing approach work does not need to be changed as much. The AASHTO load and resistance factor design specifications have several design limit states that need to be checked. The standard designs were developed to meet the Strength 1 safety design limit, the Service 2 and the live load deflection serviceability limits, fatigue limits, and the constructability requirements for the construction of the bridge. For the designs, the standard AASHTO HL93 vehicular live load was applied, but there needed to be assumptions for the dead loads on the bridge due to the owner's selection of building materials. Conservative values were assumed so that the designs will meet the different configurations that may be built. And then the designs assume a maximum overhang width of 3 feet. Now, eSPAN140 is not really design software. It is a lookup table for the bridge characteristics. Since the designs are standard, any 60-foot long simple span bridge with a 9-foot girder spacing would result in W33 by 116 rolled beams. This table shows the matrix of standardized lightest weight rolled beam shapes based on span length and girder spacing. It also gives the diaphragm spacing on the right side for the constructability design limit. And then similar tables are used for rolled beam limited depth and the homogeneous plate girder designs. eSPAN140 is a free resource. It can be found through the Short Span Steel Bridge website or directly through eSPAN140.com. There are 3 steps to producing a preliminary steel bridge design. First is to create a user account. Yep, the Alliance wants to know who's using their product. Second, input your bridge characteristics. Then eSPAN140 will produce a solutions book with the designs. Now we're going to step through the eSPAN140, but we will not pay much attention to the details. The best way to learn what eSPAN140 can do for you is to try it out with an example bridge and assess what it can do for you. So after creating an account for step 1, you are ready to design your bridge. You input the basic information. For instance here, span length. You define the number of traffic lanes, the roadway width, the parapet width, and the overhang width. Oops. You add sidewalks, if there are any. Describe the skew, the daily traffic for fatigue checks, and the design speed. And now you are ready to view the solutions book. It's that easy. The solutions book will provide rolled beam and or plate girder designs according to this chart that's shown here. For instance, if your span is 40 foot, you will get a rolled beam solution. If the span is 100 foot, you will get a rolled beam and a homogeneous plate girder solution. We're not going to discuss the corrugated steel pipe or structural shapes. We're going to look at some of those in the presentation on the 29th. The solutions book comes as a PDF file and contains the standard designs and additional information to help the owner or engineer. And we're going to again just briefly look at those here. Here is an example elevation view of a homogeneous plate girder solution. This is a bill of materials and a camber diagram for that plate girder. This is the elevation view of a rolled beam bridge. Remember, these are simple span bridges. The designs are simple. Likewise, here is the bill of materials and camber diagram. There are also drawings for the typical details shown here for the plate girder. Simple details have been designed for easy fabrication and economy. Here are the bearing, intermediate, and connection plate stiffener details. The simple and economical bent plate or channel diaphragms are adequate for these simple span steel bridges. The stud layout is shown on the elevation views, and the deck design is by the astro-empirical method. And finally, the simple elastomeric end bearings are adequate and economical for simple span bridges. So I threw in a video here. This video, and I did edit it for length, shows the first bridge built using eSPAN140 in Buchanan County, Iowa. Oh, and I better make sure I am projecting. My computer sound.
This is a story of a bridge constructed in Buchanan County, Iowa, from start to finish. The first built using a design created with eSPAN140. This project was a collaboration between Buchanan County, the Short Span Steel Bridge Alliance, and its university partners, made possible by the donations of various Short Span Steel Bridge Alliance members.
Well, basically, this is a bridge replacement on Buchanan County's heaviest traveled county road. Started out with the design, so I used the eSPAN140 computerized system for doing the design, putting the plans together. And this is something that I'm not real computer literate, but I found it exceptionally easy. We build quite a few bridges ourselves, and what this does, the eSPAN140 gives me another option. So I can start comparing prices and find out what's going to be the most economical answer in each location. And prior to the eSPAN140, I didn't have that tool and wasn't even looking at the steel bridge options.
We took the automated design out of the eSPAN140 and modeled it in our CAD workstations. We export the results of that into our computer controlled machines, and then from there the line processing happens. They come in to approximate length within a few inches, and then they are cut to exact length so that the bearing points are exact to match a survey in the field, and the distance beyond the bearing points are exact so that they can create an expansion joint at either end of the bridge. We really recommend hot dip galvanizing. It's a very low maintenance or maintenance-free type of corrosion protection. So it metallurgically bonds to the steel under the conditions in the zinc kettle and protects those beams for over the 50-year design life of the bridge up into 75 years plus.
Well, for county engineers, The opportunity to see that this bridge can be put in place very simply and very cost effectively and also have a very safe design allows them to have confidence that eSPAN140 is a tool that they can use in their county to design bridges using steel.
So if you can clear span things, then what that does for you is it eliminates the need to try and build a pier. So where if you can go up to 140-foot spans, that's tremendous. The other thing going on is the steel beams are lighter than the concrete beams. So it doesn't take the heavy equipment. If you're not dealing with some real long links, you're probably able to just set them with a hydraulic excavator rather than bringing in a crane.
Okay, so that's a little video that it's a little bit of marketing to you, but interesting video. Now, I did not discuss in this presentation, but eSPAN140 can also offer corrugated steel pipe, structural plate, and press brake tub girder solutions. And we're going to look at some of those in the January 29th presentation. So eSPAN140 is supported through the Short Span Steel Bridge Alliance Bridge Technology Center, where you can submit questions and get help in considering short span steel bridges. So to conclude, eSPAN140 will produce a preliminary design for short span steel bridges, and it is very easy to use. As we discussed before, the best way to see if it is useful for you, for your bridge needs, is to try it with an example bridge project. The Alliance also provides what are called manufacturer solutions. These are bridges produced by Alliance members that they will design, fabricate, and deliver to your bridge site. Most of them applicable for accelerated bridge construction. And we're going to look at many of these bridges in the January 29th presentation. So that completes today's presentation. We looked at the costs and life cycle costs of steel and concrete bridges. We saw that both are competitive, and owners and design engineers should consider both for short span bridge projects. We learned that eSPAN140 can produce a preliminary design in a matter of minutes that allows us to compare costs with concrete bridges easily. In the January 29th presentation, we will look at a showcase of bridge case studies. Now we're going to take questions, and I will finish up.
Thanks, Dr. Barker. At this point, we don't have any additional questions on the chat. You can type in your questions, or Dr. Barker, I don't know if you want to open up or open it up to questions directly via phone or through
Yeah, we're a small
audio.
enough group. If you want to unmute yourself and we just have a chat, let's do that. Somebody join in so we know that you're there.
Yeah, Dr. Barker.
Yeah, Tony.
Where do I go to receive credits towards my forester's degree for watching this seminar? Is it what you explained earlier?
That was actually Ray that explained the certificate for this for PDHs.
Yep.
Ray, do you want to address that one? Depends which state you're in.
Right. Thanks for the question, Tony. Each of these two presentations have been awarded category 1 credit by both the State of Maine Board of Licensure for Foresters and SAF. If you wish to get credits, email, and I put this in the chat function. I'm not sure if you can see that in your screen or not, but in the chat box. Everybody that is in attendance today, send an email to Cindy Pascal, and her email is in the chat box there. That'll make sure that we have all the accurate emails to send the certificates to, and everybody will get a certificate of attendance signed by me as the NER.COFE chair, that you were in attendance today, and you'll get your 1 credit for either SAF or the state of Maine. Most states, I'm not sure how many folks we have from other states. Looking through the attendance list here, the participants, most of the folks I recognize. If you're not from Maine, I know most states will acknowledge SAF credits as well. So you should be all set there. If you're not, let me know and we'll take care of that.
Thank you.
Hey, Ray, there's nothing in the chat box from what I see.
Okay, well, I had, yeah, I typed the chat and sent it to everyone. I will try to do
I'm
that.
not seeing anything either in the chat.
I just sent it again.
Yep, okay, there's,
You see it now?
yes.
Okay.
Yeah, we're good.
Okay. Thanks, Mike. Any other
Well,
questions?
If
Any other
there are
questions?
no more questions, we will close out today. Now, today we talked about costs, life cycle costs, eSpan. That's a good, I enjoy that presentation, but on the 29th, I welcome you back to join us then. I have lots of cool videos, lots of cool pictures of manufactured bridge systems and how they were installed with accelerated bridge construction or through county crews or and that type of thing. So join us back then and we will have more information for you.
Super. Michael, thank you again very much. And Dan, thank you for helping with the moderation and putting this on. And I know personally, I was looking forward to this one and really looking forward to the one on the 29th. And we can see some of the other things that we didn't talk about today.
You bet. Thanks for organizing this, Ray. Have a great weekend, everybody, and stay safe.
You too, Michael.
Thanks, Ray. Thanks, Dr. Barker.